This is my Calculus 1 course. Today we're going to learn the chain rule. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. The chain rule is a part of this course where students start to have some problems understanding. The good news is the chain rule is actually pretty easy to use once you learn how to do it. But typically when students first learn this, they start to have some problems, some frustration, because, there's two reasons that I think the chain rule is difficult. Number one, the notation used to describe it is a little confusing, and also students are not quite sure when to use the chain rule. So we're going to talk about that. The solution to any confusion that you might have with this is just to do practice problems. If you do 100 problems where you have to use the chain rule and you still don't understand, the only way to fix that is to do more practice problems. So that's what we're going to do today. But before we go into the chain rule, I want you to make sure that you have a picture of all these formulas so that you can have these right in front of you as we work along in the class. It's very important to understand that you need these right in front of you as we do problems today. If you don't have these trigonometric formulas, then you're just not going to be able to proceed. So please be sure you have those. Also, I would recommend creating a math file on your photo program on your phone. Entitle it math equations or math or whatever you want, and start to collect the formulas that you need and put them in that file. You can take a picture of these trigonometric identities that we are going to be using throughout this course and put that in the math file. Hopefully that's going to be a good enough resolution for you. If it's not, let me know. I can try to make that clearer. So now we're going to learn the chain rule. And so I'm going to state the chain rule, but this is probably not going to mean much to you. Again, the only way to learn the chain rule is to do practice problems. The chain rule is used when you have a function inside another function. Do you see this g of x? It's inside the f function. So we define h of x as f of g of x in this case, and that's called a composite function. The chain rule tells you how to find the derivative of the function when you have this scenario. So the derivative is equal to f prime of g of x times g prime of x. Now you can see why that notation is pretty confusing. So again, this doesn't really mean anything to us at this point. We need to do practice problems to help us to understand, but you can use these three steps to guide you through the process when you're finding derivatives using the chain rule. So I want you to get a picture of all this information here. Please get a picture of that so you have that in front of you, and we're going to use those three steps. So let's do some practice problems. Again, the only way that you're going to learn the chain rule is to do practice. If you're not sure, if you're still confused after doing problems, do more problems. If you're still confused, do more problems. If you're still confused, do more problems. That's the only way to learn the chain rule. So let's use the chain rule to find the derivative of this function. We're going to find dy over dx. But we can't find the derivative of this function because we don't know how. The reason we don't know how is because we have a function inside another function. We haven't learned how to find the derivative of an expression that fits that description. So here's how we find the derivative using what we call the chain rule. We're going to find the derivative of the outside function. Now this is the power function. So remember, when you have x cubed, the derivative is 3x squared, right? So that's what we're going to do here. We're going to find the derivative of the outside function, but we're going to keep the inside function unchanged. So we did the green part, we found the derivative of the outside function, And I'm going to just write that as 3 minus 1 just to show the steps there. So I found the derivative of the outside function, and we kept the inside function unchanged. That's the first 2 steps. The third step is we're going to find the derivative of the inside function and then multiply it by everything that we just wrote. And that's it. That's the chain rule. It's that simple. We just have to find the derivative and then simplify the expression. So you're going to be using this rule thousands and thousands and thousands of times over again. So it's very important to learn how this works. So the derivative of the purple expression is 4x cubed minus 3. So that's the derivative there. The inside function remained unchanged. And that's as far as we can simplify that. So that's how the chain rule works. And I know that this is a little confusing. Again, students have a lot of trouble understanding this. But again, once you learn how it works, it's not going to be too difficult. Now, when you're dealing with trigonometric functions, it's often difficult for students to understand which function is on the outside and which function is on the inside. In this case, x squared is the inside function and the outside function is the sine function. I know that that is kind of confusing for students, but again, as you learn more about trigonometry, you're gonna learn why that is. So step number 1, find the derivative of the outside function. The derivative of sine x is cosine x. We learned that in the previous class, right? Step number 2, keep the inside function unchanged. Step number 3, multiply all that by the derivative of the inside function. That's it. That's the chain rule. So cosine of x squared, I'm going to use brackets to eliminate any ambiguity. Cosine x squared times the derivative of x squared, which is 2x. And then we can write the 2x in the front of the cosine function to eliminate any confusion. And there we go. So that's it. That's the chain rule. So again, we're going to use this thousands and thousands of times. When a lot of students see this, they don't like it. They don't like it at all, and they want to kind of run away from it, escape it. Well, I just want to make it absolutely clear to you, you're not going to escape. You're going to do this thousands and thousands of times. Now, notice that the 2 is between the n and the x here, whereas in this problem, the 2 is to the right of the x. That's a huge difference. A huge difference. What this notation means is we're taking the sine function and squaring it. So in this example down here, the sine function is the inside function and the square function is the outside function. But up here it's the exact opposite situation. The inside function is the square function and the outside is the sine function. You can see why students would have some difficulty with this. It's kind of confusing. So we're going to find the derivative of the outside function. And you don't have to write 2 minus 1. Notice I didn't do that over here. You don't have to write 2 minus 1, but you can if you want to. So step number 1, find the derivative of the outside function. Step number 2, keep the inside function. And step number 3, multiply by the derivative of the inside function. Alright, so we have 2 times sine x to the first power times the derivative of sine, which is cosine, Remember, we learned that in the previous class. The derivative of sine is cosine. And we have 2 times sine x times cosine x. Now, I don't want to make things more difficult for you, but you should be aware that if you see a problem like this in a textbook and you want to check your answer in the back, assuming that it's an odd problem or a problem where the answer is written in the back of the textbook, you're probably not going to see your answer in this form. You're going to see it as sine 2x. And the reason for that is in calculus courses, you're expected to know just about all of this information that we learned in my trigonometry course. Now, very few calculus students actually do remember all this information. So if you don't have all this memorized, that's okay, that's normal. But eventually you're going to have to know just about all this stuff. I think I mentioned in the previous class, these formulas down here are typically not really important. Heron's formula is not really that important. This information here is not really commonly something that you'll need, but you are required to know this information here, even though it's not really commonly something that you're going to encounter, at least not in this part of the curriculum. So the circled stuff down there you may not need to know, but everything else you're going to be expected to know. And so again, if you don't know everything on this picture here, that's okay. I want you to know that calculus teachers and calculus textbooks are going to expect that you know all that stuff. So just be prepared. You're going to need to start reviewing that stuff, and as we go through the calculus curriculum, you're going to be forced to review it. So don't be scared of the trigonometry. Don't be depressed if you don't know all that stuff. You're going to have a greater understanding of the trigonometry as we move along in the calculus curriculum. Okay, so now again we have the situation where you have a function inside another function. So we need to use the chain rule. Now we're going to be using calculus here, obviously, and we learned that when you're finding derivatives of expressions that have radicals, or roots if you want to call them that, we need to change to an exponential expression before we find the derivative. Now you could enter this into the derivative formula. Remember, the derivative formula is the limit of f of x plus h minus f of x all over h as h approaches 0. You could plug this into the derivative formula, but that would take forever to figure out, the derivative. So it's easier to change this to an exponential expression and use our differentiation formulas. So now that we have an exponential expression, we can use the power rule along with the chain rule. So the chain rule tells us the first step is to find the derivative of the outside function while keeping the inside function unchanged. And again, you don't have to write 1/2 minus 1 if you don't want to, but so step number 1, step number 2, and step number 3 is to multiply all that by the derivative of the inside function. Okay, so let's simplify. We have 1/2 times 1 plus 2x squared to the negative 1/2 power, and the derivative of 1 plus 2x squared is 4x. Now, in my curriculum, I don't allow students to leave their exponents as negative numbers or fractions. And here we have both scenarios in one. So first we need to use exponent rule number 8 to turn that into a positive exponent. And then we need to use exponent rule number 9. And by the way, these numbers are from my intermediate algebra course. If you want to go back and look at the exponent rules. So we change to a square root. Okay, so we dealt with the negative exponent and the fraction exponent, and now we can multiply all this together. And we can actually reduce. So we have 2x over the square root of 1 plus 2x squared. So there you go. Now some students might say, well, wait a second, you can't have a root in the denominator. Well, if you have a situation like 1 over root 2, that's a very simple situation, and you can get rid of that root in the denominator by multiplying both sides by root 2, and we get root 2 over root 4, which is root 2 over 2, so you can get rid of the irrational number in the denominator. That's a very simple situation because you have a constant there, but here we have a variable involved, and we don't really know for sure if the denominator is irrational, and the algebra gets kind of confusing when you're having to get rid of the root in the denominator. So typically calculus teachers don't really care if you leave the root in the denominator in this situation where you have a variable. But if you have a situation, again, like 1 over root 2, well, then calculus teachers might actually care. They might tell you to change to root 2 over 2. So just be aware of that. So at this point, you might be thinking to yourself, well, when do I get to try a problem? Well, I want to do quite a few of these before you try one on your own. You can attempt any of these. You can stop the video anytime you want and attempt these, but I would just go along with me here for a few more problems before you try one on your own, because again, this can be very confusing. So it's important for you to see a number of these problems before you try one on your own. So we're going to find the derivative of the outside function while keeping the inside function untouched. And then we're going to multiply by the derivative of the inside function. That's it. It's that simple. It sounds simple, but not exactly. It's still confusing, right? A lot of students have trouble with this. So we found the derivative of the outside function, which is 5. The 5 here, and then the 4th power. We use the power rule. We kept the inside function, and then we're going to multiply by the derivative of the inside function, which is 5. Okay, so obviously you don't have to use highlighters when you do this. I'm going to put this over here. So now we can simplify, and we have 25 times 5x plus 1 to the 4th power. Alright, so there's another example. Now we're switching to y prime. That's not really anything different, it's just a different notation. Step number 1, find the derivative of the outside function. I know it's kind of hard for students to see, but the outside function is tangent. Now the derivative of tangent is secant squared. So that's step number 1, find the derivative of the outside function. while keeping the inside function. That's step number 2. Keep the inside function unchanged. Step number 3, multiply by the derivative of the inside function. That's all the chain rule is. That's all you're doing. So we have secant squared negative 6x to the 4th. And I'm going to write brackets to avoid confusion. The derivative of negative 6x to the 4th is negative 24x cubed. So it's best to write the negative 24x cubed in front of the secant function to avoid confusion. And whoops, that should be cubed. Actually, no, that's 4th. So there you go. There's another example. Again, this derivative turned into that, and the outside function is there, the inside function is there. Alright. So I know you're pretty anxious to try one of these on your own, but let's do some more problems so you can get the hang of this. Now, we don't know how to find the derivative unless we change that root to an exponential expression. At least we don't have a formula, an easy formula. So we're going to find the derivative of the outside function while keeping the inside function unchanged. That's the first 2 steps of the chain rule. Step number 1, step number 2. Then we're going to multiply. In step number 3, we're going to multiply by the derivative of the inside function. Okay, so we have, I'm just going to rewrite this, and then we have negative 2/3. And the derivative of 1 plus cotangent x is negative cosecant squared x. Of course, 1 is just a constant. 1 is a constant, so the derivative of 1 is 0. Okay, so in my curriculum, I don't allow you to leave the exponent as a negative number or a fraction, and we have both situations here. So first we're going to use exponent rule number 8 from my intermediate algebra curriculum, which tells us that we can change that to a positive exponent by bringing it down and turning this whole expression into a fraction. And then we can use exponent rule number 10 to get rid of the fraction exponent. So then we have the cube root of 1 plus cotangent x squared. And then we can write the final form of the expression as negative cosecant squared x over 3 times the cube root of 1 plus cotangent x to the 2nd power. Okay, so I know this expression looks pretty complicated, but in calculus you're going to see a lot of complicated looking expressions. So just be aware of that. Alright, so let's try, I think we have 3 more problems that we're going to do together before you try one on your own. So again, it's good for you to keep saying how this works before you try one on your own. So we're going to find the derivative of the outside function. Cosine is the outside function. The derivative of cosine is negative sine, while we keep the inside function unchanged. That's the first 2 steps. Step number 1, find the derivative of the outside function. Step number 2, keep the inside function. And step number 3, multiply all that by the derivative of the inside function. That's step number 3. That is the chain rule. So we have negative sine of cosecant x times the derivative of cosecant x, which is negative cosecant x times cotangent x. And in order to eliminate ambiguity, confusion, I'm going to write brackets and parentheses. So usually you want to write the simpler trigonometric functions first. A negative times a negative is a positive, so those go away. And there's a couple different ways that you can write these types of expressions, but you want to write them in a way so that you don't confuse things. If you write these functions right next to, or if you write these functions to the right of this function, these might be confused. You might think that they're actually inside this sine function, so you want to eliminate that confusion by writing those on the left. This is just something that you're going to learn over time as you see these problems written. So there's another example where we use the chain rule. Let's try another one of these. We're going to find the derivative of the outside function while keeping the inside function unchanged. And again, you can just go straight to 7 there, or you know, I'm just trying to go slow here and show the steps. Then we're going to multiply that by the derivative of the inside function. And that's it. That's the chain rule. Okay. So let's see if we can simplify the expression. The derivative is negative 2 secant x tangent x, and okay, so we have a couple more of these problems before you try one on your own. Here we have this situation again where we have similar looking functions, but they're actually quite different. Because here the inside function is x to the 4th, whereas here the inside function is the cotangent function. So let's find the derivative. Step number 1, find the derivative of the outside function, which is negative cosecant squared. Step number 2, keep the inside function unchanged. And then step number 3, multiply by the derivative of the inside function. So now all we have to do is simplify. We're done we're done using the chain rule. We just have to simplify the expression. So I'm going to use brackets. And this is the derivative of x to the 4th. Again, this is the outside, or the derivative of the outside function and the inside function. And finally we have 4x cubed, negative 4x cubed, times cosecant squared of x to the 4th. Okay, so now we have the situation again where the cotangent function is on the inside, but we can't really see that until we change to this notation. So now we're ready to find the derivative. We're going to find the derivative of the outside function while keeping the inside function unchanged, and then we're going to multiply by the derivative of the inside function. prime is equal to 4 times cotangent x to the third power times negative cosecant squared x. So we have 4 times cotangent to the third power x. Actually, we can write the negative out in front. And times cosecant squared x. There you go. Okay, so now it's time for you to try. So at this point you should have a good idea of how the process works, but again, students are typically quite confused about this chain rule. It takes a while to get used to this. So I want you to make sure you have pictures of all these formulas and a picture of the chain rule. And you can get a picture of these if you haven't already. Take a picture of these problems to help you, and a picture of these problems. And I'm going to leave numbers 10 and 11 in the window, and I want you to try number 12. When you come back, we'll do it together. Alright, we're back. So we can't really simplify that much more. So if you got that right, good. Try number 13, and when you come back, we'll do it together. Alright, we're back. So if you got that right, very good. Okay, now number 14 is a very, very different situation. Before you find the derivative, I would suggest that you change to this form. That's going to help you. So find the derivative of number 14, and when we come back, we'll do it together. Alright, we're back. Again, mathematicians just do it that way because it makes it so we don't have to write parentheses. So if you got that right, good. Notice that the answer here is different from the answer here because, again, you need to know which function is on the outside and which is on the inside. So you can take a picture of all these problems if you want to help you do number 15. Now remember, when we're finding derivatives, we don't really know how to find the derivative of a root. At least not, we don't have any formulas for that. So we have to change to the 1/4 power. So go ahead and try number 15, and when you come back, we'll do it together. Okay, we're back. Okay, so if you got that right, excellent. Go ahead and try number 16. When you come back, we'll do it together. Alright, we're back. So that is the final answer. So if you got that right, excellent. Okay, now we're using y prime notation, but as you know, that's the same as dy over dx, just a different type of notation. So try number 17. When you come back, we'll do it together. Alright, we're back. So if you got that right, excellent. Alright, so if you want to, you can take a picture of these problems to help you with number 18. Now, with number 18, remember, you're going to need to change the root expression to an exponential expression. So, go ahead and do that problem, and when you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. Okay, try number 19. When you come back, we'll do it together. Alright, we're back. So there you go. If you got that right, Excellent. Okay, go ahead and try number 20, and when you come back, we'll do it together. All right, we're back. So there you go. Have you got that right? Good. Let me rewrite that cotangent x. Okay. Go ahead and try number 21, and when you come back, we'll do it together. So if you got that right, excellent. Now before you try number 22, you probably want to change the form to this. So just be aware of that. Try number 22. When you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. Okay, so there's a particular type of problem that I've been avoiding, because this is where things do get a little weird when you're finding the derivative of the secant function or the cosecant function, and it's the outside function. The secant function is the outside function, so something kind of strange is going to happen here. Let's try and see what we come up with. So the derivative of secant is secant tangent. So when you write secant and tangent, you found the derivative of the outside function. The second step of the process is to keep the inside function unchanged. But notice that because we have a product of the secant function and the tangent function, we actually have to write the inside function twice. So that's kind of weird. But again, well, one way you can think about it is the inside function is the input of the derivative function. So the derivative is secant tangent. If you were to put an input into that function, you would have to put it into both the secant and the tangent function, because you have a product of both functions. So that's step number 1, and then step number 2 is to multiply by the derivative of the inside function. So yes, that is kind of a weird problem. You don't have to show all of these steps, but I'm going slow here so you know what we're doing. So the derivative, probably best to use brackets. The derivative is negative 4x cubed plus 2. Now, we don't want to write this over here with brackets because it's just not in the simplest form. So we can do one more step, and we can write the negative 4x cubed plus 2 at the very far left in front of the secant function. And that's going to eliminate any confusion. So there you go. So that was kind of a weird example. That's kind of where our process, our 3-step process, kind of doesn't make complete sense. Because in this situation, you have to think of the inside function as the input of the derivative of the outside function in order for this to really make sense. Let's try another one of these problems. Now we're finding the derivative of the cosecant function. So we find the derivative of the outside function, which is negative cosecant cotangent. and we have to keep the inside function unchanged, but we have to put it in both of these functions. So again, this is kind of strange. Again, this is where our three-step process kind of breaks down when it comes to interpreting how to do this. In this situation, you have to interpret the chain rule as the derivative of the outside with the input of that function being the inside function, and then multiply by the derivative of the inside function. That's one way to think about it. So I'm going to put the cosine function in front. So again, I know this is kind of a weird example, but I want you to try a problem like that, number 25. When you come back, we'll do it together. Alright, we're back. So if you got that right, excellent. Okay, go ahead and try number 26. When you come back, we'll do it together. Alright, we're back. So there you go. If you got that right, good. So now we have a problem that is very similar to the problems that we just did. Just a slight difference. First, we need to rewrite so we understand what's going on here. That's what that notation actually means. So we're not taking the derivative yet, so I'll take that prime symbol away. So we're going to find the derivative of the outside function, which means we have to bring that 3 down and multiply it into the -2. And of course subtract 1 from the exponent, so we found the derivative of the outside, but we kept the inside function unchanged, and now we're going to multiply by the derivative of the inside function. And so we have -6 times cosine x to the second power times -sine x. And we can do one more step, put those negatives together, and I'm going to write the sine x first, it doesn't really matter. And I'm going to get rid of the parentheses on the cosine by changing the location of the 2 power. So there you go. I want you to try a problem like that. Go ahead and try number 28. When you come back, we'll do it together. Alright, we're back. Okay, so now we're going to do problems where we have to use the chain rule more than once. And here's an example. We have a function within a function here and a function within a function here. So we're going to use the sum rule, which tells us to take the derivative of these two expressions and add them together. But as we use the sum rule, we're going to have to use the chain rule also. So let's use the chain rule here. We'll find the derivative of the outside function while we keep the inside function unchanged, and then we'll multiply all that by the derivative of the inside function. So we use the chain rule on that first expression. we also have to use the chain rule on this function here. And now that I think about it, I'm going to go ahead and just rewrite that. I just want to try to eliminate as much confusion as I can. Remember, when we have an expression like that, it's much easier to think about it as tangent x to the second power, like that. So we're going to find the derivative of the outside function. So that's the green, while we keep the inside function unchanged. And then we're going to multiply all of that by the derivative of the inside function. So we use the chain rule here, and we use the chain rule here. So now let's calculate those purple derivatives. That's going to be 3x squared minus 10 and the derivative of tangent x is secant squared x. Okay, and that's really all that we can do for that problem. I don't see any way that we can simplify that. So I want you to try a problem like that. Go ahead and try number 30. And when you come back, we'll do it together. Okay, we're back. There's multiple ways to do it. So if you got that right, excellent. So now we have another situation where we're going to use the chain rule twice. But here we have a function within a function within a function. Okay, so we have a function within a function within a function. And in that situation, again, you're going to use the chain rule twice. You don't really have to memorize this formula because, again, it's just using the chain rule more than once. But if you found the derivative of that expression, you would use the chain rule once by taking the derivative of the outside function and keeping the inside function unchanged, and then multiplying by the derivative of the inside function. But when you find the derivative of the inside function, it's a function within a function, so you have to use the chain rule again. And when you take the derivative of this, you get this, which uses the chain rule again. Find the derivative of the outside function, keep the inside function, and multiply by the derivative of the inside function. So, yeah, this is just a huge mess. But again, when you get used to the chain rule, it's not going to be that difficult. I know it seems horrible right now, but when you use this rule again and again and again, you're just going to get used to it. Now, you could do this for any composite function. If you have a function within 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 a function, it would still work. It would still work. And when you take the derivative, you would just have all these multipliers, multiplying, and the more functions within functions you have, you would just have more multipliers when you take the derivative. And so that's probably the reason that they call this the chain rule. Because when you find the derivative, it sets off a chain reaction. And you just keep going and going and going and going. So let's try an example of that. Again, you don't need to use this formula. That just kind of shows you why this is called the chain rule. But we're finding y prime. So we're going to find the derivative of the outside function, which is negative cosecant squared, and we're going to keep the inside function unchanged. So derivative of the outside function, keeping the inside function unchanged, and then we're going to multiply by the derivative of the inside function. So that's it. It's a chain rule. Again, you don't have to memorize this formula up here. You're just using the chain rule. But notice that when you find the derivative of the purple expression, we've got a function within a function. 5x is the inside function, and sine is the outside function. So you have to use a chain rule again. So let's rewrite all this stuff. And now let's find the derivative. We're going to find the derivative of the outside function, which is sine, so that derivative. And I'm just going to use brackets here so we don't have any confusion. The derivative of sine is cosine. That's the derivative of the outside function. And then we're going to keep the inside function. So step number 1, step number 2, but then we have to multiply by the derivative of the inside function, which is 5x. So do you see how we use the chain rule twice? So again, I know that's very intimidating, but even though it seems intimidating now, it's just going to be like second nature to you once you get used to this. So let's simplify if we can. I'm going to go really slow here, and we're just going to take it step by step. The derivative of 5x is just 5. And I'm going to use brackets to eliminate any confusion. So that became that. Now, I don't know if I want to use this exact same color, so I think I'm going to lighten these colors a little bit just so you see that those expressions are not the same. I don't know if that helps, but we got some slightly different colors there. Okay, so now I'm going to write the negative and the 5. Take this 5 over here, put it there. And then I'm going to write the cosine 5x and the cosecant squared of sine 5x. That's the way you want to write it to minimize confusion. It's a very confusing expression. I don't deny that, but that's the best way to write it probably. So I want you to try a problem like that. Again, you can use this formula if you want, but it's not really something that is probably going to be very helpful because it's pretty confusing. You just want to think about the general idea that we're using the chain rule twice. So try number 32. When you come back, we'll do it together. Okay, we're back. And we're done. So if you had some trouble with that, that's okay. Every student has trouble with those types of problems when they first learn them. I don't have enough parentheses. Actually, I do, and that's fine. So every student has trouble with those problems. It's okay. But again, we're just getting practice here. So have you got that right? Excellent. Okay. Let's try this problem here. We are going to have to use the chain rule twice again. And you know what? Before we find the derivative, I forgot we need to write in a derivative-friendly form. That's going to be raised to the 1/7 power if we write it in exponential notation. So now we can find the derivative, and we're going to take the derivative of the outside function, leaving the inside function alone. So that's the derivative of the outside function, leaving the inside function unchanged. And of course we're going to multiply by the derivative of the inside function. And you can use brackets if you want. So let's double check all this, make sure we have it right. Everything looks right. So we're going to rewrite all this stuff here. That's going to be -6/7. And then when we find the derivative of this, we're going to have to use the chain rule. Derivative of tan is 0, but I'm going to bring the 5 down, finding the derivative of the outside function. 5 becomes a 4. So that's derivative of the outside function, and we're keeping the inside function the way it is. And then we're going to multiply by the derivative of the inside function, which is 4x minus 1. Sorry, that's kind of sloppy. Okay. So I'm going to rewrite this stuff again. You don't have to show all these steps. And multiplying, we get 10 times 4x minus 1 to the 4th power, and then derivative of all that is 4. The derivative of that is 4, keeping the inside expression. Again, that's the outside. Sorry, my computer's going slow. So let's double check, make sure everything is right. So I'm going to take the 4 and the 10 and combine it with the 1/7. So then we have 40 over 7. I'm also going to bring this down. I'm just going to do all this in one step. I'm going to bring it down so it's a positive exponent. And I'm also going to change it into a root. So it's going to be the 7th root. And all of that stuff is going to be raised to the 6th power. And I'm going to go ahead and write the other stuff in the numerator. Okay, so there you go. So I know that's kind of complicated. We rushed forward a little bit there. But I want you to try number 34. And when you come back, we'll do it together. Okay, we're back. So, if you got that right, excellent. Okay, so here's another type of problem that you might see where we have to use the chain rule twice. But let's rewrite this so we really understand what we're doing. That notation really means that, right? I'm going to use another set of parentheses just to be clear. You could use brackets if you really wanted to. So let's find the derivative. We're going to find the derivative of the outside function. So that is the grain. As we leave the inside function alone, then we're going to multiply by the derivative of the inside function. But you can see that when we find the derivative of this, we have to use the chain rule again. So secant x over 2 to the first power is just secant x over 2. And the derivative of the secant x over 2 is secant x over 2 times tangent x over 2. That's the derivative of the outside, keeping the inside, and we should use parentheses probably, keeping the inside, and then we're going to multiply by the derivative of the inside, which is just 1/2. Remember, if you have x over 2 and you want to find the derivative, you can just write that as 1/2 x. So you're just using the constant multiple rule. Okay, and it looks like we can combine those secants. Also 1/2 times 2 is 1. So we have secant squared x over 2, secant squared of x over 2 times tangent x over 2, and that's it. Okay, so I forgot to change to dy over dx. It doesn't really matter that much, but we're just showing you the different types of notation you can see. So go ahead and try number 36. When you come back, we'll do it together. All right, we're back. As long as we try to eliminate confusion or reduce confusion. Okay, so let's do this problem together. So derivative of the outside function is negative cosecant squared. We're going to keep the inside function unchanged. And then we're going to multiply by the derivative of the inside function. Okay. So I'm going to rewrite this part. And then the derivative of cotangent x cubed is negative cosecant squared x cubed. And probably be good if we used brackets. So we found the derivative of the outside function, and we kept the inside function the way it was, and then we're going to multiply by the derivative of the inside. So again, you don't have to rewrite all this. I'm just rewriting so we can retrace our steps and figure out how to do this. So the derivative of x cubed is 3x squared. And now all we have to do is simplify the expression. So we can write the negative 3x squared first. And I'm going to write the, actually it's going to be positive because we have a negative times a negative. And then we have cosecant squared x cubed and cosecant squared of cotangent x cubed. And there you go. So that is kind of complicated. It looks complicated, but it's really not difficult. It just seems difficult. So try number 38. When you come back, we'll do it together. Alright, we're back. So that's it. So if you got that right, excellent. Now we're going to do problems where you have to use the chain rule 3 times. This is the situation where you have a function within a function within a function within a function. We're not going to do very many problems like this. They're not very common in the curriculum, so you don't have to be too worried about this, but they do appear, and so I want you to see a couple of these just so you can be prepared if you do encounter this situation. Again, this notation here is really not very useful because it just makes things more confusing, but this is really what it would look like if you have some function z of x that's a function within a function within a function within a function, and you want to find the derivative of that. Then you see what happens is it sets off kind of a chain reaction, and you start to multiply all these expressions. Again, that's why most likely it's called the chain rule. But we're not going to use this. We don't really need that formula. It just makes things more confusing to look at. Now notice how this 2 is between the n and the fraction here. That makes it so we don't have to write so many parentheses and brackets and whatnot. But it's hard to understand what's going on if it's written there. So I'm going to change the form of this before we find the derivative. So if we write it in that form, I think it would be a little easier for us to understand what's going on. So we have a function within another function, within another function, the square function, within another function. So let's find the derivative. First step is to find the derivative of the outside function, which is cosine. Remember, the derivative of cosine is negative sine. And then we're just going to rewrite the inside part. Remember, that's step 2 of the chain rule. So step 1 is the green. Step 2 is the blue. And then step 3, of course, is to multiply by the derivative of the inside function. And the derivative of the inside function is the derivative of all that stuff there. So we use the chain rule for the first time, but again we're going to use it a second and a third time because we have a function within a function within a function here. Again, don't be too worried about this because you're not going to see these problems very often. And to be honest with you, I kind of hesitate to even give you a problem like this because it's kind of intimidating. But again, this you may see this. So now we're going to find the derivative of the purple expression, and it looks like tangent is the outside function, but actually the square function is the outside function. So we're going to find the derivative of the outside function. And I'm just going to keep the brackets there, I guess. So we found the derivative of the outside function, and we kept the inside function. And now we're going to multiply by the derivative of the inside function. And the inside function is tangent negative x to the fourth over 2. All right, so let's go down to the next line. And I'm just going to copy all this stuff here. That's a lot to have to write. Now again, you're probably thinking, well, why are you going to make me write that? I don't want to write that. Well, I'm only going to give you maybe 1 or 2 problems, so again, don't worry. So we're going to find the derivative of the outside function first, which is secant squared. We're going to keep the inside function. So derivative of the outside function, keep the inside function, and then last step, the third step, is to multiply by the derivative of the inside function. So again, we use the chain rule 3 times. Okay. So now all we have to do is simplify. Well, actually, we still have to find the derivative of that expression there. So I'm going to rewrite all this stuff again. And the derivative of negative x to the fourth over 2, well, before we find the derivative of that, I'm going to change the form of this expression. I'm going to change it to negative 1/2 x to the fourth. You don't have to do that, but it helps us to see how to find the derivative. So we can just use a constant multiple rule. You don't want to use the quotient rule for that. So the derivative of negative 1/2 x to the fourth is negative 2x cubed. Now I'm going to use brackets to avoid confusion there. And now let's go back and make sure we have everything right. Now we can change these green 2 minus 1s to just 1 power. We don't really need to write 2 minus 1 when we go on to the next steps. And we don't have to write a power at all when we get to this step here. And so now we can multiply this, this, and this. So negative times a negative is a positive. So, and then 2 times 2 is 4. So we have 4x cubed. And I'm going to write the simplest trigonometric functions first. So tangent negative x to the fourth over 2 times secant squared of negative x to the fourth over 2, and then times sine of tangent negative x to the fourth over 2, and we need more parentheses, squared. So looks like that is the final answer. Whoops, that should be y prime. So it's good to double check all this, make sure we did it correctly. Don't be afraid to take a moment and just look over all that. Everything looks right. And if we want, we can take this 2 here and we can move it back to the convenient place here, so we don't have to write that extra set of parentheses. That's the whole point of writing it there, is so we can make our expression, we can write our expression without those parentheses. So there you go. So I want you to try a problem like that. I want you to try number 40, and when you come back, we'll do it together. Okay, we're back. And there you go. That is the final answer. So I apologize for making you do that problem. But again, these are just the type of problems that you may see. So I don't want you to be caught off guard if you do see one of these types of problems. These are probably way more difficult than problems that you're going to see. So don't be too worried about this. So you may be wondering, what is the proof of the chain rule? There are different types of proofs that you can see out there, but here's one proof. So let's say that a function is a function within a function. If you want to find the derivative of that composite function, you use the derivative formula, of course. And r of x is just whatever that expression is, so we just rewrite it. H is just rewritten, and the only hard part is finding r of x plus h. Remember, r of x plus h is exactly the same as r of x. The only difference is, instead of x, you write x plus h. So r of x plus h is f of g of x plus h. So now we have to do something tricky. We have to multiply both sides by this expression here. But this expression is just equal to 1 because the numerator and the denominator are the same, right? So that expression is equal to 1. You're just multiplying by 1. That's the fundamental principle of fractions. But then we do something tricky again, and we kind of rearrange things using the commutative property of multiplication. And then we use limit law number 3 because we have a product here. And so the limit becomes the limit of the first expression in the product times the limit of the second expression in the product. And you see that this is very convenient here. That's just the derivative of g of x. That's just g prime. Now, this is a little bit more difficult to understand. At this point in my curriculum, you may not be able to quite understand why that's equal to f prime of g of x. But we can study that in more detail later if you want. Again, you're not really required to know these types of proofs, so you're not going to be tested on this. But believe it or not, this expression is actually f prime of g of x. This is just the derivative written in a different form. Here we have h. Here we have g of x plus h minus g of x. But remember, when we derived this formula, we had to use the slope formula, and in this case, the x's don't really cancel out as they do here, but it's still the derivative. But again, we can go over that in more detail later on. But this is kind of an idea of how the proof works. So that was the class today. If you'd like to take screenshots of all the work that we did to help you with your homework or to study for tests, go ahead and do that now. Here's screenshot number 1 and number 2 and number 3 and number 4, number 5, number 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. But don't go before you get your homework. Remember, if you don't do homework, all the homework, completely and correctly and neatly and keep it in order in your binder, then you're going to learn absolutely nothing in this entire course. So get a screenshot of this first page and screenshot number 2 and screenshot number 3 and number 4 and number 5. But remember, if your homework is not correct, then it's useless. It's a waste of time. So you have to check your answers. Here's the answers. Be sure to do that homework completely and correctly, and I'll look forward to seeing you in the next class.